This is Bob Capetta from the University of Illinois at Chicago, and this is yet another example of power series. We want to use the power series approach to find a series representation for this function. And you'll notice this is not in the form a naught over 1 minus r. But what is? Is there some way for us to get to a naught over 1 minus r? There is a way for us to get there by using an integral. The integral of f of x will look like that, and we can use that to construct a series for f. So I define a new function g of x, which is the integral of f of x, is the integral of 5 over 3 minus 2x squared. This will be done with the u substitution. U will be 3 minus 2x. Take the derivative with respect to x of u, and the derivative with respect to x of 3 minus 2x. The derivative with respect to x of u is du dx, and the derivative with respect to x of 3 minus 2x is negative 2. With my technique, I like to solve for dx, so multiply both sides by dx. Du is negative 2 dx, and du divided by negative 2 is dx. We'll replace the 3 minus 2x with u, and we'll replace the dx with du over negative 2 to do this integral. So there's our original. Again, 5 over u squared du over negative 2, which we can pull the negative 5 halves out in front. So I have negative 5 halves integral of u to the negative 2 du. Using the power rule, integral of u to the negative 2 is u to the negative 1 over negative 1. So negative 5 halves times negative 1 will be positive 5 halves. U to the negative 1 is 1 over u plus c. So what do we get? We get 5 halves times 1 over u, or 5 halves times 1 over 3 minus 2x plus c. We're going to choose to ignore the c for now, but you'll recognize 5 halves times 1 over 3 minus 2x is in that a naught over 1 minus r form. And that will enable us to do a power series for that function. Once we have a power series for g, we can construct a series for f. So indeed, we're going to define that g of x function as 5 halves times 1 over 3 minus 2x. Recognizing indeed that g of x is in that a naught over 1 minus r form. So ignoring the constant, let's define this as our g of x function, the g of x function we want to use. So it's 5 halves times 1 over 3 minus 2x, or 5 halves over 3 minus 2x. We want this in a naught over 1 minus r form. Our problem is that 3. We'll need to divide the numerator and the denominator by 3 to turn that 3 into a 1. So 5 halves divided by 3 upstairs, 3 minus 2x divided by 3 downstairs. And we get 5/6 over 3 over 3, 1 minus 2x over 3. Our goal was to get this in a naught over 1 minus r form, which we have. So the a naught will be 5/6. The common ratio will be 2x over 3. We see that. Now once that's the case, we can construct a geometric series for g of x. 5/6 plus 5/6 times 2x over 3 plus 5/6 times 2x over 3 squared plus 5/6 times 2x over 3 cubed, etc. And our exponents, 3, 2, 1, 0, this is going to start at k equals 0. That's going to be the sum as k goes from 0 to infinity of 5/6 times the common ratio, 2x over 3 to the k. So we have constructed a geometric series for g of x. As long as we've done that, let's find the interval of convergence for this one. We used a geometric series strategy. We need the common ratio to be between negative 1 and 1. That's all. So negative 1 is less than 2x over 3 is less than 1. Multiplying by 3, negative 3 is less than 2x is less than 3. And then dividing by 2, negative 3 halves less than x less 3 halves. We use a geometric strategy, so we do not have to check the endpoints. If the common ratio is 1 or negative 1, the geometric series will diverge. So that's our geometric series for g, as well as the interval of convergence. But what about f? What was our relationship? Well, we started with f, and we thought the integral of f might be in a form that we could use. And that's what we had. The integral of f that we're calling g was in a naught over 1 minus r form. If g is the integral of f, how do I get f back? If I'm working with g, how do I get f? Take a derivative. So f is simply the derivative of the g function. We have the power series for g, so a series for f will be the derivative of the power series for g. So it's the derivative of this sum as k goes from 0 to infinity of 5/6 starting point, 2x over 3 to the k. Well, the derivative of the sum is the sum of the derivatives. We know that. So our f of x will be the derivative of this. Now I'm simplifying the algebra first. 2x to the k is 2 to the k over x to the k divided by 3 to the k. So I guess I wanted to make that a little simpler first. And then I said the derivative of the sum is the sum of the derivatives. So I pulled this derivative operator past the sum operator. But as far as x is concerned, 5 is a constant, 6 is a constant. As far as x is concerned, 2 to the k and 3 to the k are constants. So they can come out to the left of the derivative operator. It's a derivative with respect to x, and I want the derivative of x to the k, which will be kx to the k minus 1. So what I've done now is I have determined a series that defines the function f. Now can we find the interval of convergence for f? Will it be the same as g, or will there be a slight difference? So we're starting with this, and if we want to find the interval of convergence, we're going to appeal to the ratio test. So I'm going to need the absolute value of a sub k and the absolute value of a sub k plus 1. Everything is positive here, so the absolute values sort of happen automatically. All right, so a sub k will be 5 times 2 to the k over 6 times 3 to the k times kx to the k minus 1. We have that. Now to get a sub k plus 1, replace all the k's with k plus 1. 2 to the k will become 2 to the k plus 1. 3 to the k will become 3 to the k plus 1. K will become k plus 1. X to the k minus 1 will become x to the k plus 1 minus 1. And of course, x to the k plus 1 minus 1 is simply x to the k. Using the ratio test, we will take a sub k plus 1 absolute value divided by a sub k absolute value, and then take the limit as k goes to infinity of that ratio. So it's this divided by this. This, of course, is a sub k plus 1 divided by a sub k divided by that. If we want to divide fractions, change the division to multiplication and take the reciprocal of the thing on the right. So we come times 6/5, 3 to the k over 2 to the k, 1 over k to times x to the k minus 1, which is what we have here. Now let's think through our algebra. 5 divides out 5, 6 divides out 6. 2 to the k plus 1 over 2 to the k. There's one more 2 upstairs. I'll have a 2 upstairs. 3 to the k upstairs, 3 to the k plus 1 downstairs. One more 3 downstairs. How about the k's? What do we have there? K plus 1 over k, fine. How about the x's? X to the k upstairs, x to the k minus 1 downstairs. So there's one more x upstairs. So what does that give us? The 5's cancel, the 6 cancels. 2 to the k plus 1 over 2 to the k is 2. 3 to the k over 3 to the k plus 1 is 3. K plus 1 over k is here. X to the k over x to the k minus 1 is just x. Of course, it's absolute value, so we write that as absolute value of x. With the ratio test, we look at the limit as a sub k plus 1 over a sub k absolute value goes to infinity. What will happen there? As k goes to infinity, k plus 1 over k is going to go to 1. And we're left with what? Pulling out the 2/3, that's fine. We're left with 2/3 times the absolute value of x. So, with the ratio test, it will converge if that limit's absolute value is less than 1. So I will need 2/3 x to be between -1 and +1. If that's the case, multiply by 3/2, so I'm going to get -3/2 is less than x is less than 3/2. Now we use the ratio test, and when you use the ratio test, you've got to recognize that it's inconclusive if that limit is 1. So we really should go ahead and check the endpoints to see if they may converge there. So let's go ahead and do that. So here was our definition of f of x. Our endpoints are 3/2 and -3/2. So I want to evaluate f of 3/2. So I replace the x with 3/2. Now 3/2 to the k minus 1 is 3 to the k minus 1 over 2 to the k minus 1. How does this algebra work? 3 to the k minus 1 over 3 to the k, I have one more 3 downstairs. 2 to the k over 2 to the k minus 1, I have one more 2 upstairs. So we have 5/6, 2/3 k. Does that converge? Certainly not. By the divergence test, as k gets large, this whole thing gets large. It goes to infinity. If the sequence does not converge to 0, the series diverges by the divergence test, or the nth term test. So no, 3/2 is not in the interval of convergence. Let's take a look at -3/2. So if I want f of -3/2, I'll replace this x with -3/2. So 5 times 2 to the k, 6 times 3 to the k times -3/2 to the k minus 1. Whenever we raise a negative number to an exponent, I like to break that up into -1 to that exponent times the number times 3 to that exponent. Because once we're there, now we can do our division. 3 to the k minus 1 over 3 to the k, I'll have one more 3 downstairs. 2 to the k over 2 to the k minus 1, one more 2 upstairs. But it looks like I am missing my -1 to the k minus 1. Let me quickly fix that. So indeed, we have -1 to the k minus 1 there as well. So can we simplify this at all? Do we think this converges or diverges? 5/6 times 2/3 times k over 1 times -1 to the k minus 1. It's bouncing. Negative, positive, negative, positive, negative, positive, negative, positive. But does that sequence go to 0? It does not. K keeps getting bigger and bigger. So pulling out the multiples, that gives us 5/9 times -1 to the k minus 1 times k. That certainly diverges. So -3/2 is not in the interval. We check both endpoints. 3/2 led to a divergent series. -3/2 led to a divergent series. So neither 3/2 nor -3/2 is in the interval of convergence. And just something to notice, it was 5 over 3 minus 2x squared. When is the denominator 0? That's when x is 3/2. So there's no way x equals 3/2 can work for this function because it's not in the domain. That leads us to an asymptote. So it shouldn't surprise us that 3/2 is not in the interval of convergence. We have our function there, our f of x, written in that form as a series, and we've identified our interval of convergence as x is between -3/2 and +3/2. And that will conclude this lesson.